Okay, welcome back. In this lesson we will see the famous Monte Carlo simulation of stock prices, the usual graphs which look like a forest of lines which you find sometimes on newspapers. Okay, let me change the power option of my computer to silent, otherwise you will hear only the woo. First of all, we have to talk about random numbers. Okay, because Monte Carlo simulation, well, the name Monte Carlo comes from the place Monte Carlo, right? It's not a person, so you can easily guess why does it use random numbers. So random numbers exist in Python. They are inside NumPy, so we import NumPy, and here we show you how to create a uniform distribution of random, how to create a vector, so an array of random numbers from a uniform distribution. So it's np.random. Np-random is the, let's say, the sub package of the package NumPy, which creates a random number. The function is uniform, obviously. Okay, you have to supply parameters. If you have taken any course of statistics, you should know better than me that a uniform distribution has two parameters from where to go. It's the typical rectangular distribution. Or if you're not familiar with a uniform distribution, go to Wikipedia and look for it. So this time we will go from -1 to +1 because that's what we use. So we'll generate random numbers between -1 and +1 equally distributed. Okay. Then you have to specify how long the array will be. Unfortunately, for technical reasons, this thing goes between round parentheses, so 15. So I will create now 15 random numbers. Okay, you can see an array. Okay, as I told you, an array for your level, it's just a list, nothing else. So you can see random numbers between -1 and +1. Okay, same thing, but this time we will take them from a normal distribution. So as you can easily guess, you just change uniform to normal. For the normal distribution, you have to specify the two parameters of the normal distribution. Again, here, if you don't have any idea what is mu and what is sigma in a normal distribution, please look on Wikipedia and try to get a clear idea of what is parameter mu, the average of the normal distribution, and what is parameter sigma, the standard deviation of the normal distribution. We'll take, this is a normal distribution centered around 0 with a 1 standard deviation. So you will see that most of the values are close to 0. Well, actually, yeah, many values are close to 0, but some of them are far away. It's pretty skewed. Let's retry. Can you see a lot of negative numbers? Let's retry. Okay, now we have a lot of positives, so it makes sense. So if you put many numbers, you should see that. Okay, they are perfectly centered around 0. Okay, so this is how we build uniform and how we build random values taken from a uniform distribution or normal distribution. You can take them from any other distribution, doesn't matter, it's up to you. This produces an array. You can produce also a matrix of random values. This is useful because later on we'll have to use a matrix of random values. So, for example, from a uniform distribution, let's take a 7 by 15 matrix. So it will generate, you see, it's a matrix. That is the first row with 15 elements, second row with 15 elements, and up to 7 rows with 15 elements. So in Python you can easily generate arrays and matrices with random numbers, which are the numbers that we will use for Monte Carlo simulation. Okay, I imagine you have never seen what is Monte Carlo simulation. Let's go slowly. Okay, I wrote everything, so you can just read. We start from the definition of daily log return. Pay attention, it's the log return. The daily log return is the definition. Natural logarithm, or in this case natural logarithm is fine, of the price of today divided by the price of yesterday. I remind you that this is exactly equivalent to logarithm of price of today minus logarithm of price of yesterday, because it's one of the features of logarithm, which you should have studied at the third year of high school, according to Italian high school programs. Okay, now we apply the exponential to this side, and we get exponential of the daily log return equal price today divided by price yesterday. You put price yesterday on the left side, and you get that the price of today is the price of yesterday by the exponential of the daily log return. The daily log return, pay attention, of today, because if it were the daily log return of yesterday, we would have invented a machine to predict the price of today given the date of yesterday, which would be impossible. So this is the daily log return of today, not of yesterday. Okay, so if we just know the daily log return of today, we can exactly determine the price of today using this formula. Unfortunately, obviously, we don't know the daily log return of today. However, we know the typical distribution of the daily log returns. We have data about all the past days. We have a lot of data about all the past days. From those data, we can determine the distribution of the daily log return. Okay, which distribution, how do you determine it? It's up to you. We'll make some examples here. So we build now a model for the daily log return, which, I repeat, we don't know because it's the daily log return of today, which is a drift plus volatility model. So we assume that there is a drift, which is a general trend, which usually for stock prices it's going up. It's very rare that a stock price has a general trend going down, a stock. So drift represents a general tendency. Okay, so we take the drift, for example, equal to the average daily log rate, okay, which of the past, obviously, which is positive. And just to be on the safe side and avoid over predicting it, but it's just to be on the safe side. Honestly, if I were going to do it professionally, I doubt I will put it here. Professionally for myself. Professionally for a bank or a financial intermediary, I will put it. Okay, just to be on the safe side, let's reduce it a little bit, subtracting the variance of the daily log return divided by 2. Well, it's just a rule of thumb, it's not a rule. It even doesn't respect the units of measure because, these are all numbers, yes, okay, no, it respects, okay. But using the variance and not the standard deviation doesn't make me happy. However, typically people just put this minus half of the variance of the daily variance divided by 2 to just stay on the safe side. Okay, then we have the volatility part. The volatility will be determined with a random number. So if we keep only the drift, we'll have a constant daily log return, and you will see a graph with a line which will go up exponentially because it grows exponentially. One goes over the price of yesterday, so it will go up exponentially, not because there is an exponent here, okay, but because one price is determined by the price of the previous day, so it will go up automatically exponentially if you just keep only the drift. So if you keep a deterministic approach. We'll take instead a stochastic approach, so a random approach, and the volatility, we estimate it, this means estimate, with the standard deviation of the log rate, okay, multiplied by a variable. A random variable. This is a random. A random variable is nothing else but a mathematical variable which does not have a fixed value but has a value which varies randomly, like this one. Now you understand why I introduced the random function, the random package in NumPy. Okay, so, and this variable, it's a variable which it's around 0. So, has, we say in statistics, has a 0 expected value. So it fluctuates around 0, exactly like this 2. This one fluctuates around 0, uniformly from -1 plus 1. This fluctuates around 0, non-uniformly, but normally with a 1. Okay, so it's a random variable which fluctuates around 0. The important thing is that it fluctuates around 0. the more you take it fluctuating, well, the more the volatility will be. And pay attention because everything is also multiplied by the standard deviation of the log ret, because if we are talking about an asset which has a huge standard deviation, you have to amplify this volatility a lot. If it is an asset with a low standard deviation, historically, obviously, you can never say anything about the future, say anything for sure about the future. You will have a smaller standard deviation. Okay, so this is our idea. I will start now slowly to build a forecast for the price of, let's say, tomorrow. Okay, and then I will set up a tool to forecast the price of tomorrow next, 2 days after, 3 days, 4 days, 5 days, up to 200 days. Okay, since if I forecast only one price, well, it strongly depends on the value that you get from here, and it can be anything. I will forecast instead 20 different prices using 20 different values every time. So at every step, I will forecast the volatility using 20 different random numbers. So it's different even at every step. And so you will see 20 lines going erratically everywhere. Let's start. So import all the things you should import. Now let's get, let's get the prices. As usual, Procter & Gamble. We get the price, this time only from 2009. Only the adjusted closing price. Okay, the adjusted close price. Let's take a look at them always. Okay, yes. Okay, we have to calculate the log ret of these prices. I bet that in NumPy there is a tool to calculate this thing here automatically. Exactly as there is a tool to calculate the percentage change, probably there is a tool also to calculate this one. And let's also take a look at it. Okay, first one is none as usual. Okay, let's take some values. Okay, makes sense. A positive average, it is the standard deviation, the variance. Okay, and now let's calculate the drift. The drift is log ret.mean. You can see that mean, standard deviation and variance are robust functions. It means that if they find a none, they simply skip it. We say minus log ret.var divided by 2. And I would like also to see it. Okay, we have a drift. This is the drift. You can see it's somehow smaller than the average log ret. Okay. Oh, sorry, I dd. Okay, the volatility on the other hand is a distribution. So volatility equal log ret std multiplied by now a random number. So npy dot random dot, let's start with a uniform -1 + 1, and we need, I will do it with 20 simulations. So if I just type 1 here, it's not really a random number. Okay, it's random, but it's 1. So I type 20, so I will show you 20 possible volatilities. So volatility is an array. So okay, this is the volatility. You can get the same with a normal distribution. Okay, and now finally tomorrow price is equal to a price of today, which is, how do I get the price of today? It's a series dot they can get it like this. Today is the 2022-2-24. Let's see, just to see whether I can get. There are other ways to get it, but no. It's stuck. Prices. No, you cannot extract. 23. Okay, so it's not tomorrow price, but it's today price equal. This is the price of yesterday. Today is not over because I'm recording in the morning. This is the price of yesterday. Okay, you can get it like this. Okay, or you can get it like this. -1. I remind you. Oops. What happened? Help. What's this? Okay. -1. I remind you that 0 is the first element, 1 is the second, 2 the third. If you type instead -1, it's the last element. Okay. Multiply by, you look at the formula above. Here it is. Price of yesterday by expected exponential of the log return. By the price of yesterday, this is the... Yes, that's the price of yesterday. The exponential, put some spaces, np.exp. The exponential is part of the NumPy package. And as usual, we have the drift plus the volatility. Pay attention, however, that the volatility is an array. This means that if you sum a number to an array, Python is so intelligent that it will create an array. If you calculate the exponential of an array, it will be an array. And so all this will be an array. So don't expect one price, expect a forecast of 20 prices according to the value of volatility. So today price. Early. What happened? -1. See, yes, sorry, not lock, but prices of -1 directly. Okay. Okay, so these are the forecasting for today price. According to our model, which uses as drift the historical logarithm, the historical average logarithm, minus a half of the variance, and which uses as volatility the standard deviation of the logarithm multiplied by a uniform distribution between -1 and +1. Okay, so these are the data. If you rerun this part, you will get different results. Look, I rerun it, and now look, the first one was 157.47, 155.61. It's random, that's why. Okay, so it's usually good to do even more than 20, perhaps 100 simulations, because each one will give you a different number. Okay, and this one was the prediction for today. Now I want to set up a tool which, given the historical data I have up to yesterday, will build a prediction for today, but also for all the days in the future. So all this 20 prediction will have another prediction, so there will be another row with 20 prediction for tomorrow, then another row with 20 prediction for Monday, because tomorrow is Friday for me, and then another row of 20 prediction for Tuesday, and so on. Okay, so how to do? We now want to build prediction for 250 days. It's a little huge. Therefore, we build 20 volatilities for each day. So we don't keep the same volatility numbers, but we rebuild them for each day. So it will be different for each day. Okay, let's go slowly. So we can keep the drift we have before, so we can keep all the things that we have before. The drift stays the same, so drift stays the same. Okay, we just rebuild the volatility log ret std by np dot random dot uniform -1 +1, and now we build 250. So we build 20 data for 250 times. Okay. And here you can see. No, these are 20 data, there are the dots for 250 times. Okay, very well. Then I build this part here. Where is it? I lost it. Here, this part here. Okay. So let's call it exponential of daily returns. Exponential of daily return. So it's again a matrix with 20 simulations for each day and 1 row for each day. So 250 rows, and pi.exp drift plus volatility, and let's take a look at it. Okay, very well. I would like, now currently it's an array, I would like to put it into a data frame because it's an object that we are more used to. So let me put into data frame. So let's call EDR, exponential of daily returns, equal data frame. You just, if you have a matrix as an NumPy array, you can just put it into a data frame like this. What happens? Data frame. Sorry, pandas data frame. Okay, so now it's something which I'm much more familiar with now. You have 20 here. You can see 20 simulations from 0 to 19 for each day. These are the simulation for today, tomorrow next. These are the simulation for the daily return, or better, the exponential of the daily return. So how much the price moves. Okay, so you see, for example, that according to simulation, the price of today is slightly more than the price of yesterday. According to simulation, the price of today is slightly less. Okay, I think that it's pretty obvious. These are the movement from the price of the day before up to the price of the next day. Okay. If you hear strange noise, it's my neighbor who is sewing something, I don't know, or doing something else in his bed, I don't know. Okay, very well. Now we have to get the start price, which is the price of yesterday, so the price which starts our simulation. Okay, let's take a look at it. Okay, this is the price which starts our simulation. And now, finally, we go on with the future prices. Okay, we prepare a data frame like this one, but which instead of containing the exponential of the logret, will contain the future prices. So we prepare future prices equal a data frame, an empty data frame. Okay, this creates an empty data frame. Okay, I want the empty data frame to be for the moment full of zeros. Okay, how do I build a data frame full of zeros? I have to use the NumPy zeros creates a. So this creates a matrix full of zeros with 251 rows and 20 columns. Why 251 and not 250? Well, because I will include as first row the price of today. So the first row will contain the price of today, which will be the same for all the 20 simulations, because all the 20 simulations the price of yesterday, which will be the same for all the 20 simulations, because all the 20 simulations start from the price of yesterday, which is something which is already well known. So I built this one, which is, let's see, pay attention to the double parentheses. They are necessary for technical reasons which I don't want to explain here, because this is I I don't want to explain why it are necessary. It's beyond the scope of the course. Okay, so you can see it's just a data frame full of zeros. Now we put as future prices dot iloc 0. I remind you that iloc 0 is this row here. Okay, and I set it equal to start price. Okay, I set an entire row equal to a single number, something which theoretically is impossible, but Python is so intelligent to understand that if I set an entire row equal to a single number, it has to put that number in all the, can you see? It has to put the number in all the values. So we start from the price of yesterday. Okay, and now I have to do the simulation. So I have for each day, starting from here, to take the price of the day before, so shift 1, the price of the day before, and multiply it by this value here, by the estimated log ret of the day of today, this value here. Okay, I could do it vectorially, prices. Okay, I don't have to estimate all of them. I will skip the first one, so dot iloc 1 colon. This will skip the first one. So we start from 1 up to 250. So there are exactly 250 equal to future prices dot shift 1. And this, if you do shift 1, it means that this one will be none, this one will be 155. Okay, let me see first if this one works. No, there's an error, it's complaining. 251, 250. Okay, so I have to iloc 1 colon. Okay, this one works, so I take the future price shifted by 1, always starting from the second one, so this one will become none, this one will become 155, and it's what I want to start with. Okay, multiply by EDR, which is this one. This one has exactly 250 rows, so it's fine, it's exactly like that. Let's see whether it works. Okay, it doesn't work. Why? EDR has exactly EDR. Do I have to put iloc also here? Okay, anyway, even if you put iloc here, okay, even if you put iloc here, it doesn't work, and I'll show you why. Okay, a lot of zeros. Well, it's a little messy now. Okay, can you see a lot of zeros? It has calculated only the first one. Why? Well, because this time, this is one of the few cases in which doing the thing vectorially means all together without a loop going through the rows one after the other doesn't work. Because you cannot do all the rows at the same time. If you try to do row 4, estimating it using row 3, currently row 3 is 0. So you cannot, the result of the estimation is 0. So you can't do it vectorially, as I wrote here. So you can't do all the rows at the same time. Unfortunately, this is one of the things in which must be done sequentially. So row by row, very slowly. Don't worry, we will not. So in theory, you should do it row by row, which means you should do. Let's restore future prices as it was before. You should do future prices of iloc 1 equal future prices shift 1 iloc of iloc 0 multiply Okay, should be this one. Can you see? Estimated a set. Then this one becomes 2. This one becomes 1. This one becomes 1. Estimated the third one. This one becomes 3. This one becomes 2. And this one becomes 2. Don't worry, we will not go on forever. Okay, because we will convert it into a loop. So for I in range so I didn't want to introduce loops in this course, but for this specific example it was absolutely necessary. This thing here simply creates sequentially I 1, 2, 3, 4, 5 up to 250, not up to 251, just up to 250. And so it will do sequentially 1, 2, 3, 4, 5, 6. Now first of all restore future prices as it was originally, and now let's go. Okay, now you can see it has calculated all of them. And now finally we can plot it and takes a while, takes more than a while. Okay, this is what you get. Oh, but may I have? No, I may not have enough. Okay, the legend is totally useless, so let's remove the legend. As you can easily imagine, legend equal none removes the legend. Okay, and here you have, so you have the simulations using a uniform distribution. If you redo it using a uniform distribution, they will be different. If you do them using a normal distribution, they will be more concentrated around the average value. So the normal distribution tends to concentrate them more around the average value. For the simulation, we can do that. We can see that 2 simulations go very bad. Okay. However, 18 simulations are at least, you see, at least in a little gain. So most of the simulations have a little gain. It is after 1 year. And there are 1, 2, 3, 4, 5 simulations which represent 25% of probabilities with a huge gain. Huge gain means you double your initial capital. So the price for Procter & Gamble doubles in 1 year. Very good result. So 25% of possibilities to double the result according to our model. And 75, let's say here 10% of possibilities to lose something, and the rest you stay more or less, staying positive, but not double. Okay, let's redo it using a normal distribution. It's pretty easy. You just change here from uniform to normal. Okay, 0, 1. If you want to make the normal more concentrated, just choose 0.5. This is the standard deviation of the normal. If you want to make the normal more spread out, just take 2. Okay, don't modify it to 0, because otherwise you will create a volatility which doesn't have a 0 expected value, which is against all the possible financial and statistical laws. Okay, let's... Oh, and just now rerun everything. Click, click, click. Easy peasy. You see? The big advantage of using this kind of programming language, just now you have to click as I'm doing. It will take a while to regenerate all the... No, not even take a while. Let's see. Open. Okay. Well, I told you it will be more concentrated, and I see that it's not. Seems more uniform this one than the other one. Okay, the problem is that 20 simulations are not too many. If I were doing it professionally, I would use 1,000 simulations, but your computer will explode. But you can use 100, for example, simulation. Let's say here the distribution is pretty uniform. So funny that the distribution of the volatility only, and not of the returns, was normal. But in my case, at least, the distribution is pretty uniform, with approximately half of the cases losing some more, not half, 1, 2, 3, 4, 5, 6, 7, perhaps 8, 9, no, 7 losing something and 13 gaining something, but only 4 of them double. Well, not so bad. Here you have some extremes. This is because you have more extremes here, because the normal distribution officially it's not bounded. So in the normal distribution you could have a volatility which goes from minus infinity to plus infinity with a very small probability, while the uniform distribution it's bounded between minus 1 and plus 1. Okay, this was everything for the Monte Carlo simulation. If now I manage to shut down, bye bye.